In the last lecture, we talked about the fact that an ideal gas is a big collection of independent subsystems where each subsystem is a single molecule. So the overall partition function is q to the n power over n factorial, where q is a single molecule partition function. And of course, the n factorial is present because in a gas, the molecules are indistinguishable. Then we saw also that the molecular partition function is a translational partition function, a rotational partition function, a vibrational partition function, and an electronic partition function. So not only does the big partition function factor into a whole bunch of little ones, each little one also factors into a whole bunch of still smaller ones. And the first one we're going to talk about is the translational partition function, which accounts for the fact that molecules can run around in their box and there are quantum states associated with running around in the box. It will turn out that the translational quantum states are the most important for statistical mechanics. They're not terribly important from a quantum point of view, but there's a lot of them. And that's what counts when you're doing statistics. So let's talk about the translational partition function in the context of a particle in a box model. We're going to put our gas molecules into a box, and the box is going to have a side length of A. I'm going to call that the length of the side. So the volume of the box is just A cubed. All sides are the same. And we've seen that we don't really need to deal with all the molecules. Dealing with just one molecule at a time is enough. So we're going to have our molecules running around inside the box. And because they're quantum particles, they have a de Broglie wavelength. So they're all quantum waves in addition to being molecules. And we're going to see that that de Broglie wavelength is an important part of the statistical result that we get. All right, if we write down the quantum Hamiltonian for a particle in a box, right away you'll see, here it is down here, that it breaks into three parts, one for each dimension in its own right. And those three parts are independent. Each one depends only on its own variables, and it's a sum of them. And that means that the wave function factors into three different wave functions, one for each dimension. And that means that not only does the big partition function factor into a bunch of one molecule partition functions, and then each one molecule partition function factors into a whole bunch of separate subsystem partition functions, but even the translational partition function factors into three parts. And so the translational partition function is just the cube of a one-dimensional particle in a box partition function. So all of it boils down to us just finding the one-dimensional particle in a box partition function. Before we do that, we're going to do that next. Let me just note that normally when we talk about a particle in a box, for most students, I think what you're familiar with is electrons in a box. Electrons are light. Molecules are quite a bit heavier. That means their de Broglie wavelengths are a lot shorter. Let's calculate how short they are. That's going to be an important number later on anyway. So here's the de Broglie wavelength formula, the Planck constant divided by the momentum of the particle. Our particle, quote unquote, is an N2 molecule moving at 500 meters per second. That's a typical speed. In fact, that's the RMS speed for a gas molecule at room temperature. Then plugging in all the numbers, doing the arithmetic, we get that the de Broglie wavelength for that particle is about 3 times 10 to the minus 11, or about meters, or about 0.3 angstroms. So it's not infinitesimal compared to the size of a molecule, but it's shorter, smaller than the size of a molecule, and therefore very much on the microscopic scale. All right. That's our background. Now let's consider the one-dimensional particle in a box. So we've got a box, its length, its side A, its length A, that's the side of our three-dimensional box. If we solve for the energy eigenvalues, we get that they are h squared divided by 8, mass of the particle m, times size of the box a squared, and a quantum number n, which is an integer that starts at 1 and goes to infinity. So for every value of n, we get a different energy. Since this is a particle in a box, which is just about the simplest quantum system there is, we can also solve for the wave functions, but it turns out we don't need them. You never need the wave functions for statistical mechanics. So that's really nice. Instead of having to do all the work that you would need to do in order to get wave functions like you do in quantum mechanics, we can just ignore the wave functions. If we can get the energies, that's good enough. That's all we need for StatMech. All right, the partition function for a one-dimensional particle in a box is then a sum over all the quantum states for a particle in a box of e to the minus beta energy for each quantum state. In this case, each quantum state is labeled by our integer 1, our integer n, and goes from 1 to infinity. And then the energies are these guys over here, so plugging that in place of the energy, E sub n, this is the sum that we have to do. Notice it's an infinite sum. Unlike all the examples that we've worked up to now, which only had a finite number of states, and in fact only had a relatively small number of states usually, this system has an infinite number of states. Almost all quantum systems have an infinite number of states, so this is not at all unusual once we start dealing with real systems. So we have to do an infinite sum, and we've got to get something meaningful out of it. We can't do this term by term, obviously. We've got to do something better than that. And so what we're going to do, well, sometimes infinite sums like this can actually be just turned into finite algebraic expressions. We'll see that with the vibrational partition function, for example. But in this case, doing this particular sum straight out mathematically turns out not to be easy, so we're going to do an approximation. We note that if you calculate the gaps between different particle in a box quantum energies, the energy gaps, say, between level 0, or energy 0, and energy 2, you can do the calculation. It's just the difference between the two energies. And for a box that's rather large for the microscopic scale, a 10-centimeter box, a 10-centimeter box means there's 1,000 centimeters cubed in the box, which means it's a 1-liter box, which seems like a good, reasonable size. So for a 1-liter box, the gap between the quantum energy levels is 10 to the minus 46 joules. It is tiny. For comparison, the energy available, the thermal energy that's available around room temperature is 10 to the minus 21 joules. Normally we would think of that as being a tiny number, but it's huge compared to this number over here. And if you take the ratio of those two, if you take the size of the gap divided by the available thermal energy, you get 10 to the minus 26. In other words, the available thermal energy is enough to utterly swamp the gaps between these quantum levels. And so we're going to treat them like a continuum. Rather than worrying about the discrete levels that are actually present, we're going to treat this n quantity, this quantum number n, as a continuous variable, and we're going to change this discrete sum into a continuous integral. So we're now integrating. I've also changed the lower limit here from 1, from n equals 1 to n equals 0. That's also a good approximation. So from 0 to infinity, integrating over n of our Boltzmann factor, e to the minus beta, e sub n, with all those constants in there. If we do that, again, this is a standard integral. It's relatively easy to do. And this is the result. That's our quantum one-dimensional particle in a box partition function. This quantity out here is the size of the box. This quantity here is important, and let's look at that a little bit more. It turns out that if you look at the units for this quantity in the square brackets, it has units of 1 over length. If it were SI units, it would be 1 over meters, for example. That means that 1 over this quantity should have units of length, and we can call it a length. And in fact, what we call it is the thermal de Broglie wavelength. And in fact, physically, it comes from the de Broglie wavelength of each of the particles. So when we were talking about the de Broglie wavelength of the nitrogen molecules up above, this is why. The de Broglie wavelength is going to show up again, does show up again, when we're talking about the partition function. We'll calculate this quantity explicitly. We'll put numbers in there and actually get numbers out for this in a little while, but suffice to say for the moment that it's a small quantity. What this means altogether, taking this as 1 over the de Broglie wavelength and that as the size of the box, is that the partition function for a particle in a box for translational degrees of freedom is really simple in the end. It's the size of the box divided by the wavelength, the de Broglie wavelength, which is effectively the size of a quantum state. And so this ratio is just the size of the box over the size of a quantum state. That's the number of quantum states that fits in the box. So here's our one-dimensional box. Each one of these is 1 lambda. And here's how many lambdas fit in the box, and that's Q. And the reason I have taken so much time talking about this is that it turns out this kind of thing is what you always see with every partition function, for every kind of motion. The partition function is approximately, always approximately, the number of quantum states that fit in the appropriate box. For the translational degrees of freedom for a particle in a box, the box is obvious, and it's a literal box, but with every other kind of degree of freedom, for example, for rotations, there's also some kind of box out there. It isn't always obvious what the box is, but if you look a little bit, you'll usually find that you'll always find that there's some kind of box that's confining your quantum system, and there's a wavelength, a de Broglie wavelength of some kind that goes with that. And so you can always talk about how many quantum states fit in your box. For rotations, for example, the molecule can spin around on its axis, but always it's going to be on the surface of a sphere as it's spinning. The two ends will be on the surface of a sphere as it's spinning. And so the box is that sphere. And the rotational partition function will be the number of quantum states that fits into that box. We'll see how that works when we get to the rotations. That's actually the next topic. If I have vibrations, then the box is the range of possible stretches and compressions that the vibrating molecule can undergo, and that's your box. And so we're going to see that same pattern over and over again. All right. So for the full translational partition function, remember it's the cube of the one-dimensional particle in a box partition function. And so it's a cubed over lambda d over lambda cubed, and a cubed is just the volume of the box. So it ends up being the volume of the box, which is the thermodynamic volume, so there's a thermodynamic variable already showing up, divided by lambda cubed, which is the volume of one little tiny 3D quantum state. And so the full translational partition function is just the volume available to the molecules divided by the volume of one quantum state. And that leads us to the question of how big this thing is. How small are those little quantum states? How big is that volume? How many quantum states are there? For a single molecule, remember this is for a single molecule, not for Avogadro's numbers of molecules, just for a single molecule. How many quantum states are there? Let's do the calculation now, finally. First of all, here's the cube of the de Broglie wavelength, so you could call it the de Broglie volume, I guess. And I put a bunch of numbers in and played around with units and stuff to make it a little simpler formula. It's 5.3210 divided by the molecular weight of the molecule in question, the temperature, to the 3/2 power. And all the units down here are going to cancel these units, and so the units you're going to get out are nanometers cubed. So this formula is going to give you the de Broglie volume in nanometer cubed units. Here's the equivalent formula for the de Broglie wavelength itself. We won't look at that as much. So for nitrogen at 300 degrees Kelvin, the de Broglie wavelength cubed turns out to be just about 7 times 10 to the minus 6 nanometers cubed. That's the size of one quantum state, very small, right? A nanometer is already a small thing. Nanometer cubed is a small thing. And this is only, about 10 to the 5th, 1 10 to the 5th, 1/100,000th of that nanometer cubed. So that means Q trans is equal to the volume. For 1 liter, that volume is how many nanometers cubed? Well, it's 10 to the minus 3 meters cubed, 10 to the minus 9, 10 to the plus 9 nanometers per meter. 10 to the 9 cubed is 10 to the 27. So, and that's times 10 to the minus 3, so 10 to the 24 cubic nanometers in 1 liter. That's what goes up here, and divided by 7 times 10 to the minus 6 gives you about 10 to the 29 quantum states for 1 molecule. This is not the number of quantum states in the whole ensemble of Avogadro's number of molecules. This is the number of quantum states for 1 molecule. So the number of quantum states overall for the entire system is utterly enormous. It's this to the 10 to the 23rd power, so a serious number. All right, so bottom line, there are lots of translational quantum states. The reason there are so many translational quantum states, you can see it in the calculation up here. It's because the volume available, the box these molecules are in, is macroscopic in size. And the volume per quantum state, the de Broglie volume, is very microscopic in size. And so you're going to get a lot of quantum states. You're dividing a macroscopic value by a microscopic value. All the other degrees of freedom in the molecule, the rotations and the vibrations and the electronic degrees of freedom, they have boxes that are already microscopic. So you'll get a fairly large number of microstates, but it's in the thousands. It isn't 10 to the 29. And so the number of microstates in these other degrees of freedom is much smaller. And what that means overall is that the translational microstates tend to dominate the overall partition function. And here's the bottom line for us chemists. This is why translational entropy plays such a huge role in chemical equilibrium. Let's look at that a little bit. Here's a chemical reaction. Our usual abstract chemical reaction. A times A plus B times B goes to C times C plus D times D. The chemical potential for A, we already know what that looks like. It's a standard state chemical potential plus an extra term, and that term comes from the translational entropy effects, or from the translational quantum states, if you like. We'll derive this just a little bit down below, in fact, and so we'll see exactly that this activity term that shows up in all the chemical potentials does in fact reflect the translational quantum states. When you put that into the usual thermodynamics to get out the free energy change for reaction, you get another term that's got a combination of these activities, right? Powers of activities. That's also a translational entropy effect. And when you solve for equilibrium, what are the equilibrium concentrations going to be by setting K equal to Q here? That's nothing but translational entropy effects again. And so translational entropy effects are huge, and therefore they have a big effect on all of chemistry. All the equilibrium calculations that we've ever done throughout our careers, both you and I, are ultimately boiled down to mostly being due to translational entropy effects. All right. So that is all there is to say for the moment about the translational partition function. But it turns out that this is enough. We've only got one of the partition functions that we need for the full molecular partition function, but that's already enough to say a lot, because for monatomic ideal gases, the translational partition function is pretty much all there is. And so we're already in a position to do the thermodynamics of monatomic ideal gases. We know a lot about that already. Let's see how it compares. Let's see if we can get everything out like I've been claiming. So, first of all, the overall molecular partition function is Q trans times Q rotational times Q vibrational times Q electronic. But there are no rotations and no vibrations for an atom, obviously. So these guys are both just ones. And the electronic partition function is usually just 1, too, because the energy gaps between states, electronic states, are usually so huge that there's no population up even in the first excited state. It's all down in the ground state. So this is usually also, at least at room temperature, this is usually also just a 1. And that means that the molecular partition function is just the translational partition function, roughly, to a good approximation, in fact, for noble gases, for monatomic gases. So we can put our result that we have already into our formula for the full partition function for the whole set of n molecules, or n atoms in this case. And so Q trans goes in there. And then we plug in what Q trans is, V over lambda cubed, and that gives us our full expression for the full partition function for a gas of noble gas molecules. First thing to point out before we go any further, let's look at the variables that this thing depends on, because those variables are going to be things that all of our thermodynamic quantities depend on too. I've said before that in general, the canonical partition function depends on temperature, volume, and mole numbers. Those are the natural variables for a T-bath open system, a system that's only got a T-bath. And if we look at things, there's N, right? N, capital N here is just the number of moles times Avogadro's number. So whenever we see a capital N, we're also seeing a mole number N. And so there it is. There it is again. There it is again. So it appears in several places. Volume appears and temperature appears. And notice that there's nothing else. All the rest is either molecular properties like the mass here, or fundamental constants like h bar, like Planck's constant, or Boltzmann's constant, or 2 pi for that matter. So T, V, and N really are the natural variables, and they really do show up in this now explicit formula that we have. What do we do next? Very first thing you should always do when you have something like this is calculate the fundamental potential for the system in question. So for a TVN system, a T-bath open system, the fundamental potential is the Helmholtz potential. All we got to do to calculate that is take minus kT times the logarithm of the Q that we already have. That means plugging in the molecular Q to the nth power divided by n factorial. And then doing algebra, the next step in the algebra gets you this. You've got this log of n factorial. We use Stirling's approximation for that. That gives us that log of n factorial is approximately equal to n log n minus n. Plug that in and do some algebra, and that gives us that the Helmholtz free energy is minus nkt times the logarithm of the molecular partition function divided by n, the number of molecules, plus 1. We haven't said anything yet about what this molecular partition function is. Everything I did in this last little bit here holds for all ideal gases. So this is a good formula or a good result for all ideal gases. Now let's plug in our particular molecular partition function, Q trans. And if you do that, then here's our expression for the Helmholtz free energy. That's not of great interest in and of itself. We could plug numbers in here and we get a number out here, but honestly the numerical value of Helmholtz free energy isn't the most interesting thing. What's interesting about the Helmholtz free energy is that you can use it to get all other thermodynamic quantities. So let's see how we do that. Well, what are the quantities we want? Let's get some equations of state. The equations of state are closely related to the Helmholtz free energy. For example, the pressure is equal to minus the derivative of the Helmholtz free energy with respect to volume, holding temperature and mole numbers constant. Notice how these variables match up so nicely with what we actually have up here, right? We have T, V, and N up here. And because we've set everything up right, because we're using the right fundamental potential and everything, those are exactly the variables we get down here in the quantity and the derivative that we need. So we need to take the derivative of our expression for Helmholtz free energy that we derived up above. And if you do that, and skipping the algebra, it turns out not to be very hard, you get that P is equal to nkt divided by V. But remember that N is just the number of moles times Avogadro's number, and K is just the gas constant R divided by Avogadro's number. So Nk is just equal to little n times R. And that means that this relationship is nothing other than the ideal gas law, PV equals nRT. So right away, our Helmholtz free energy has given us one of the equations of state for a monatomic ideal gas like this, the ideal gas law. What about energy? We can do the same thing. We know from our general stat-mech relationships that the average energy, which is the same thing as the thermodynamic energy, is minus the derivative with respect to beta of the logarithm of our partition function, but the negative of the log of our partition function is just the Helmholtz free energy divided by kT, which is just this function here. It's just the expression above with the kT that used to be there divided out. And so the energy, the thermodynamic energy of our system is, I've factored this n out, it's a constant as far as this beta, this derivative is concerned. We need to take that derivative. That turns out to be, well, I've expanded it all out here. You can look at the algebra yourself at your leisure. When you take the derivative, notice that doesn't depend on beta, that doesn't depend on beta, that doesn't depend on beta, that doesn't depend on beta. The only thing that depends on beta is right there, so it's a pretty easy derivative in the end. And that gives us 3/2 nkt, which means that our equation of state for the energy is just 3/2 nRT. We've seen that relationship many times. It's the standard equation of state for the energy, for the thermodynamic energy for a monatomic ideal gas. Once we've got the energy, we can get the heat capacity. All we have to do is take a derivative with respect to temperature to get the heat capacity, and that gives 3/2 nR. I think everybody will recognize that that's the heat capacity. The heat capacity at constant volume, notice, because this is a system where volume is being held constant. That's the heat capacity at constant volume for a monatomic ideal gas. We used that many times earlier in the thermodynamics section. Finally, the big one and the most interesting one for us, the chemical potential. This requires a little bit more work, unfortunately, but let's do it. The chemical potential is, again, just a derivative of our fundamental potential, the Helmholtz free energy, this time with respect to mole numbers, n, which means we have to take the derivative with respect to n of all that stuff. That's A again. And if we do a little bit of algebra on that, then we get the following, that it's a leading term that doesn't depend on concentration-like things, and another term that involves the logarithm of something that looks like concentration. It isn't exactly concentration yet because it's the number of molecules, not the number of moles divided by volume. But that should be closely related to concentration because if this were mole numbers divided by volume, then it would be molar concentration. And we know that the number of molecules is just the number of moles is just the number of molecules divided by Avogadro's number. So clearly we've got something that's starting to look like activity here. We can do a little bit more work and make it turn into exactly activity. To do that, we take this quantity n over v, which is the molecule density, actually. We write it as n moles times Avogadro's number divided by v, and then we insert a 1, right? This is the standard state molar concentration divided by the standard state molar concentration. Then we put one of those standard state molar concentrations in there, we move the other one over to this side, and we end up with molar concentration divided by standard state molar concentration, and that is activity. Times some other stuff, and we'll see what happens with that. All right, so there's our relationship. We plug that into this expression up here, up above, do a little bit more algebra, and we get out, in fact, something that is identical to our standard chemical potential equation of state. This stuff out here is just the standard state chemical potential, and there's the RT log activity term that we always get with these kinds of equations of state for chemical potential. So I put a little check mark there. That's, again, the standard equation of state. Furthermore, the stat mech has now given us an expression for the standard state chemical potential itself. We didn't have that before. That was just a pure fudge factor constant before. Now we actually have it in terms of molecular properties. And so let's look at it. Here's our de Broglie wavelength cubed, or our de Broglie volume. That's what goes in here to our standard state expression. And when we do a little bit more algebra, we get this for the standard state chemical potential. And it's a bunch of constants, and I won't plug into those constants right now. The only thing I want to do is point out that all those constants depend, well, they depend on temperature here, but apart from that, the only molecular property, the only thing that reflects the fact that this is a noble gas versus any other molecule is the mass of the molecule in question, or the atom in question. So and that's true for all these standard state, for these standard equations of state, right? There's no molecular properties in there. There's no molecular properties in there. There's certainly no molecular properties in the ideal gas law. And the only place where the identity of these molecules even shows up is here in the standard chemical potential. And the only thing that even shows up there is the mass. It's the only thing that any of these ideal gas molecules show up. It's the only thing that shows up in any of these ideal gas thermodynamic properties. All right, so just to finish this section, before we move on to the next thing, I said earlier, I've said several times actually, that this quantity, the canonical partition function, when it's considered to be a function of these three natural variables, will give us complete thermodynamic information, but for the first time now, I've actually gone through all the details of what that really means. I imagine people have always been wondering, what the heck does he mean by all thermodynamic information? Well, now you know. In the calculation above, the partition function has given us, first of all, the fundamental potential. And from that fundamental potential, we've been able to get all that other stuff. We got all the equations of state. And once we have all the equations of state, we can derive a whole bunch of other things. For example, one of the things we did derive is the heat capacity. And if we wanted to, now that we have all the equations of state, we could get, for example, the isothermal compressibility or the thermal expansion coefficient or any other thermodynamic property that we like. And so the first thing here, the fundamental potential, tells us all the equilibrium behavior of the system. It allows us to predict equilibrium states. It allows us to predict which way the system will change if we make some disturbance or if we release a constraint on the system, if we let the pressure go or something like that. The fundamental potential, which is, remember, related to the total entropy for both system and surroundings, tells us all about which way the system will change when an equilibrium change is happening, and about what the equilibrium state is. And all these other things tells us everything about all the properties of the system. And that's a pretty good approximation or a pretty good listing of what it means to say that we have all thermodynamic information about the system. In addition, the partition function also allows us to calculate probabilities for individual microstates. So not only do we have complete thermodynamic information, we also have complete statistical information about the system. So the partition function is a really central, really important quantity. As I said earlier, it's the goal and target of a great amount of effort among people who do statistical mechanics, and now you can see why.